Hi everyone. In this video I'm excited to introduce GreenInfraIQ, a new web-based modeling tool for green infrastructure based on OpenHydroQual API. GreenInfraIQ allows you to basically select a template for a model of a green infrastructure or other water systems, then enter key system parameters, and then run dynamic simulations to analyze the performance over time. What I'm going to do is that I will basically show you how to use GreenInfraIQ to model a bioretention system. I have posted videos showing how to create models of bioretention system using OpenHydroQual plug and play or the model wizard. Now I'm going to show you how to do it web-based, basically using GreenInfraIQ. This is the diagram of the model that I want to develop. Basically, you have a contributing impervious catchment. The model basically route the flow into a bioretention system. The bioretention system consists of a surface ponding, engineered soil layer, an aggregate storage layer, and then native soil underneath the aggregate storage layer to essentially a fixed head boundary condition, which can be your groundwater, can be the depth at which you are not interested in tracking the water anymore. And then you have an overflow and underdrain pipe that go into a catch basin, and then the catch basin empties to the receiving sewer system, which is also represented using a fixed head boundary condition. Okay, so let's get started. So in order to, first of all, to reach this website, you got to go to greeninfraiq.com. So greeninfraiq.com will get you to this page. So I have several model templates. I'm planning to add more as we move forward, but currently we have 5 templates. We have a bioretention system with evaporation or evapotranspiration. You have a bioretention system which is simpler. It doesn't have it doesn't have evapotranspiration. There's a stormwater pond model, an activated sludge, simple activated sludge model, and a bioswale. What I'm going to do is that I will use the bioretention with evapotranspiration. Now, if you want to be conservative and not account for evapotranspiration, you can go with the bioretention system without evapotranspiration, which is this one. So I'm going to click on this. So it gets me to this page. Basically, as you can see, we have different tabs indicating different features of the bioretention system that I'm planning to model. There are default values for most of the parameters. Put them. I realize that's better for guiding the users what the range of the values should be and so forth, and what they mean. I'm going to adopt some of these default values as I'm showing this basically creation of this model. But anyhow, okay, one thing about GreenInfraIQ is that you don't need to provide any time series data for example, precipitation or the weather data that is needed for calculating the evapotranspiration based on the Penman equation. What it does is that it actually grabs the data from OpenMeteo API automatically based on the location of the site that we specified by providing longitude and latitude, and also simulation start date and end date. So basically it automatically goes and gets the weather data and that it needs, and then it does the calculation, and then you can later on download those data. So okay, let's get started. So I'm just going to enter some parameters. I'm going to explain the parameters here. So what I'm going to do is that I will do the simulation, I don't know, for 1 year from 2012 to 2013, and then I'm gonna, this longitude and latitude is related to Baltimore Airport, but you can of course change the longitude and latitude based on your site. And then there is this evaporation correction factor. That's because of the fact that basically the Penman equation assumes that you have open water. In reality, you may have shading, you may have things that prevent air, wind, and so on. So basically, we need a correction factor to correct for those things. Now you use this as a sensitivity parameter, change the values and see how it affects your results. But I'm going to leave the value at 0.5. That means all the evapotranspirations that are calculated using Penman equation are multiplied by 0.5. So then the next tab is model geometry. So this is actually the number of cells layers underneath the engineered soils is basically discretized too. So basically here in this diagram you see that we have these 4 layers. So this tells how you want to discretize the native soil essentially to get to the groundwater. And in this case I'm just going to keep it 3, even though it may be a little rough. Then we have the depth of engineered soil medium. So that's the engineered soil medium. The depth is 0.4 meters, and all the units in this template is SI units, with time being days, but I can create some other templates with other units. The depth to groundwater is basically depth from the surface to the groundwater, from the surface, which is assumed to be 0 or datum, to groundwater. So our assumption here is that the groundwater is 3 meters deep. Water table is actually 3 meters deep, but this necessarily doesn't have to be groundwater. It can be just it may imply the fact that we want to just model 3 meters of soil column and we don't care what happens after that. Then so this tab is about contributing area. So the area of impervious contributing area. So this is the information that is used to calculate the runoff, the flow that goes into your bioretention system. So here, I don't know, I'm just going to change this to, let's say, 2,000 square meters. The slope of the impervious contributing area, of course, the slope of this, so that's used to calculate the flow based on the kinematic wave equation. So the slope is, I assume, this 1%. Let's just change that to 2 per thousand. The effective Manning roughness coefficient of the impervious surface area, this may be a little too high for the sheet flow, so I'm just going to change that to 0.03. And then you have a catchment average width, and that's also needed to calculate the flow. Basically what it is actually the width of your catchment perpendicular to the flow direction essentially. So that's that, and then I can click on next and it'll go to the next tab. So what we have is essentially it provides the relationship between head and storage in your pond. So what it does is that actually uses the surface area of the pond at 0.1 meter depth. So if you have 0.1 meter of water, what's going to be the area? And then it calculates that to calculate the alpha and beta in this relationship between storage and water depth. So actually alpha is calculated using this value, and the beta you provided. So the value is 2. That means, I don't know, the exponent in this equation is actually 2 for calculating the relationship between storage and water depth. Now let's just, I don't know, I'm just going to make this area 200 square meters, which is quite big, but anyhow. Then okay, let's go to the next one. So if I click on next, this is the properties of the aggregate storage layer. So what's the depth of the aggregate storage layer? So this depth, the aggregate storage layer, and the porosity of the aggregate storage layer. Let's just make the porosity make the material a little more porous. So that's what we have, and then so that's all we have. And the next one is the catch basin. I wouldn't really change it. It really doesn't matter. This is actually the properties of this catch basin. So I assume that the area of the catch basin is 1 square meter, and then the catch basin invert or catch basin depth is actually 1 meter. So it's actually the bottom of the catch basin is 1 meter below the surface. Let's go to the next one. So this is the properties of the under drain pipe. A lot of them you don't have to change them. It doesn't really affect your results that much. So that under drain pipe, you can provide a Manning roughness coefficient, the diameter of the under drain pipe, and the length of the under drain pipe. So what's the length of the under drain pipe from the farthest point to the catch basin, basically. So I'm gonna assume this length is actually 20, and then the under drain pipe diameter is 0.2 meters, which I think is 8 inches roughly. Then the next one, okay, this is something that is not entered. So the next one is basically the overflow is actually represented using a weir. So and then for the weir we need a rating curve. So if it's a V-notch weir, for example, I mean if it's modeled as a V-notch weir, it's not. But anyhow, the beta value will be 2.5, and then this is the coefficient. Now the coefficient may be a little low in this case. 1000 is actually low because our flow units are in cubic meters per day. So I don't know, I can just make it 5000, but it's basically overflow only happens if the water depth gets to the crest elevation of your weir. So let's say the crest elevation, for example, if it's 20 centimeters above the ground, then I'm going to enter the basically 0.2 meters. That's going to be the crest elevation. So anytime the water depth goes above that, you'll have overflow. Then next one, okay, something else. Basically, you can use. So this is the physical parameter of engineered soil medium. Okay. Now, if you know the soil texture, now in this case, engineered soil mediums are kind of a special type of soil with high hydraulic conductivity. But if you know this type of soil, you can actually use this drop-down menu to select the soil type. I'm going to just keep it as sand because that's the closest to engineered soil in terms of high hydraulic conductivity and so on. But if you're really more realistic, you may want to increase this, for example, to a larger number. Again, the model results is not too sensitive to this value because the hydraulic conductivity of engineered soil typically doesn't really control the flow that much unless it's actually much smaller than these numbers. So anyhow, when you pick the soil type, what it does is that it basically assign the values of your Wangen-Eckton parameters too. So Wangen-Eckton alpha parameter, N parameter, the saturated moisture content, and the residual moisture content. So now we can just go with that one, and then here this is the physical parameters of the native soil. So the native soil underneath, that has a high impact on how much infiltration actually happens through your bioretention system. So in this case, I'm going to actually go and change this to clay, or maybe, I don't know, if you pick different type of soils, you'll get different values, right? So I'm going to go with clay. So it basically populates the Wangen-Eckton parameters, and that's it. We are all set. The model is built. So all we have to do is to click on create model and then wait for the simulation to be done on the server. It's going to take some time, so you got to wait because the model is actually being executed for 1 year over the server, and the data needs to be transferred to your your computer. So it may take some time, but anyhow, let's just click. Your cursor will turn to this hourglass, I mean depending on what the default of your operating system is, and then you're just going to wait for a while until you get the results. Okay, now we have the results ready. So when you get the results, a graph will pop up right here, and then some data that you can download. So let me explain this. So basically the results, the basically graphs representing the outputs of the model, are organized in tabs. So in this case, I grab certain outputs, including, for example, evapotranspiration rate from soil, and that's cubic meters per day. right? Total evapotranspiration. As you see, this kind of periodic behavior is due to, you know, day and night effect. Then you have inflow to the bioretention in cubic meters per day. So that's how much water went to the bioretention system. And then, okay, so next we have the overflow. So no overflow happened. So basically the design of our bioretention system was such that the water depth never got to 0.20 during that period of time, during that 1 year period of time. So we had no overflow. This is the total outflow, so total flow out of the bioretention system during the simulation time, and then I can look at the under drain flow. But the under drain flow and the total outflow are the same because no overflow happened. But total outflow is actually the summation of overflow and under drain flow. So that's what we have. And then you can do certain things. First of all, you can actually download all the time series data that were populated, were actually retrieved from the API. So basically, if I click on these links, it's going to give me a CSV file, and that's our relative humidity. For example, this is the relative humidity that was used. So I can actually open it in Excel as a CSV file and look at the data. And if I want to do, you know, run the model using the desktop version of OpenHydroQual, I can actually use this data. Same thing, I don't know, you can get the precipitation data, and this data is in the format that is usable directly in the desktop version of the OpenHydroQual. You can get all the outputs that we got here, you can get them in a text format. So basically these are all everything that was outputted and you know, transferred to your computer for visualization. But anyhow, we have the evapotranspiration, inflow, overflow, total outflow, under drain flow, and so forth. And then you can also download the OpenHydroQual model. So let's do that. So if I click on this, it's going to download the model. So it's basically saved as model 1 OHQ in my downloads. And I can go into the desktop version of OpenHydroQual and open it. So basically I'm going to go to my downloads. I guess it should be okay here. I have a lot of files in my downloads, so it takes some time. Okay, so basically this was model 1 that I just downloaded. I can actually open it. I got some errors because the addresses to the weather data are based on the server, so I need to fix them. I need to manually download all those, you know, weather data the way I mentioned, and then you got to go to for example, I don't know, here for evapotranspiration, and then change this address to the file that we downloaded. For example, for this one, for relative humidity, temperature, and so on. But this is the model. If I go and, you know, fix the weather data, same thing with precipitation. I need to provide the precipitation file, download it and provide it, and run this. I should get the same exact results. Thank you for watching. Look for my future videos about OpenHydroQual.